In the last class, we have discussed few things like Bolzano's intermediate value theorem or Bolzano's location of roots theorem, intermediate value theorem, then there was fixed point theorem and so on. Right? Now today we will apply some application of all these theorems, especially that one Bolzano's location of roots theorem and intermediate value theorem. I hope all of you have go through this lecture video which I had uploaded in YouTube, that theorems proofs. Now today we will apply this theorem to solve problems. Okay, write down example 1. Prove that there exists x belongs to open 0 comma pi by 2 such that x equals cos x. Prove that there exists x belongs to open 0 comma pi by 2 such that x equals cos x. We have to prove it. Okay. Proof is very easy. This is actually the application of Bolzano's location of roots theorem. So here, check this one. We have to prove if x equals cos x. So we are choosing a function fx equals x minus cos x. Okay. Over the interval 0 comma pi by 2. Now both the function x and cos x, both are continuous over this interval. That means the function fx is also continuous over this 0 comma pi by 2. And tell me the values of f0 and f of pi by 2. Compute these two values. Yes, this is minus 1 and this is pi by 2. Minus 1 is less than 0 and pi by 2 is greater than 0. That means from here we can write f0 into f of pi by 2 is less than 0. That means this and this are of opposite sign. Right? So we got a function f which is continuous over the interval 0 comma pi by 2 and at the end points they have opposite sign. So all the conditions of Bolzano's location of roots theorem is satisfied. So what we can conclude by Bolzano's location of roots theorem? What we can conclude? What is the conclusion of that theorem? There exists some point C belongs to the open interval such that f equals 0. That means C minus cos C equals 0. That is C equals cos C. So the question is proved. The answer is proved. That means we need to find some x belongs to 0 to pi by 2 such that x equals cos x. This C is our required x, right? So this C belongs to open 0 comma pi by 2 is the required x such that x equals cos x. Okay. This is how we apply these theorems. Next, write down example 2. Let f be continuous in an interval I and does not vanish anywhere in I. Then prove that f has a constant sign in I. Let f be continuous in an interval I and does not vanish anywhere in I. Then prove that f has a constant sign in I. We have to prove it. Now f does not vanish, that means f don't take the value 0 over this interval, that is fx never is equal to 0 on that interval. So we have in our hand two conditions. Number 1, f is continuous on that interval I and fx is not equal to 0 for all x belongs to I. Right? We need to prove that f maintains a constant sign throughout I. That means if we draw the graph like this, suppose this is our I. Suppose this is I, then throughout this sign the graph will take a constant sign, either positive or negative. That means either f will look like this or look like this, not like this. Okay. If this happens, then somewhere f is positive and somewhere f is negative. No, that can't be happen. We have to prove f is either like this or like this. We have to prove it. We have these two conditions in our hand. F is continuous over I and fx is not equal to 0 over I. So we are choosing, if possible, there exist 2 points alpha comma beta belongs to I such that f alpha comma f beta are of opposite signs. That is f alpha into f beta is less than 0. We are choosing, if possible, we are taking this. Now close AB, this one, alpha comma beta, consider this one. This is obviously subset of I because we have chosen alpha and beta from I. Now this is a closed and bounded interval, and given that f is continuous over I, that means f is also continuous over this. Okay, and we have taken f alpha f beta less than 0. Then we can apply Bolzano's location of roots theorem. So what we can write by that theorem? We can claim there is some c belongs to this interval such that fc is equals to 0. So there exists some c belongs to here, open interval such that fc equals to 0, right? But given in the question that f does not vanish anywhere in I. Now alpha comma beta, this open interval, obviously subset of I. So we got one point C belongs to I such that FC equals to 0, which is a contradiction of the given fact, which is a contradiction of the given fact that F does not vanish anywhere over I. Right? So our assumption was wrong. That means there cannot be 2 points alpha and beta such that F alpha F beta are of opposite signs. That means the function F takes the same sign throughout the interval capital I. Okay? This proves the question. Moving to the next example. Example 3. F from close 0, 1 to R is a continuous function, and F assumes only rational values, and F assumes only rational values if F of half equals K, where K belongs to Q, then prove that F is a constant function. F is a constant function given by Fx equals K in 0, 1. Okay, first let's try to understand the question. It is saying that F from 0, 1 to R is a continuous function. Okay, this is number 1 condition. Next, F assumes only rational values. This is number 2 conditions. Next one is the value of F of half is given. F of half equals K. Obviously K will be a rational number because F assumes the only rational values. Now we have to prove that F is a constant function throughout this interval. That means whatever point you take, the value will be K. That is Fx equals K in 0, 1. We have to prove it. We will obviously prove it by contradiction. So if possible, let F is not a constant function in 0, 1. That means F will take some other value other than K, right? So there exists some point, say alpha belongs to that interval. Obviously alpha will not half. Why? Because the value of F of half is already given. F of half equals K, and we want to find some point where the function is not taking the value K, taking some other values. So there exists some function alpha, some point alpha belongs to the domain 0, 1, obviously which is not equal to half, such that F of alpha equals beta, and which is not equal to K, right? Now it is given in the question that F is continuous in close 0, 1. And we have chosen that alpha belongs to close 0, 1, right? So suppose this is this and this is our half point. Okay, we have chosen alpha between close 0, 1 and alpha not equal to half. We don't know where alpha lies. Alpha might be here, it might be here also, right? So whenever f is continuous in that interval, that means this is also continuous either in that interval or in that interval, whatever the position of alpha becomes depending on that. So we can write f is continuous in either alpha comma half or half comma alpha, because we don't know what is the position of alpha. It is greater. I'm rejoining within a minute, okay? Just stay there.